Mars is close enough to feel almost reachable, but far enough away to remain one of the most dangerous places a human being could ever try to live. It is the planet we keep imagining as our second home. The red world on posters, in movies, in mission plans, in billionaire dreams, in science fiction cities under glass domes. When people talk about the future of humanity, Mars is almost always there, waiting in the background like a promise. But the more carefully you look at it, the more uncomfortable the question becomes. Because Mars is not just a smaller version of Earth. It is not a desert waiting for tents, roads, and greenhouses. It is a cold, airless, radiation-battered world where the ground is toxic, the sky is thin, the water is frozen, and one small failure could turn a habitat into a tomb. Before we begin, if you enjoy calm journeys through the deepest questions in space, take a second to subscribe, leave a like, and comment where you are watching from, and what time it is right now where you live. It helps this channel reach more curious minds around the world, and it is always fascinating to remember that while one person is watching at midnight, someone else may be watching under a morning sky on the other side of Earth. Today, you are watching the Just About Space channel, talking about, could humans actually survive on Mars? And by the end of tonight, the answer will feel very different from the simple yes or no that most people expect. Because the truth is this: a human can survive on Mars. But not because Mars is friendly, only because humans are very good at building tiny islands of Earth in places where Earth should not exist. Let's begin with the most direct version of the question. Imagine that a human being appears on the surface of Mars with no spacesuit, no habitat, no oxygen tank, no pressure protection, and no help. Just a person standing on the red dust beneath the pale Martian sky. What happens? The answer is not dramatic in the movie sense. You would not instantly explode. Your blood would not violently burst out of your body in one clean cinematic moment. But you would be in a lethal environment immediately, not after hours, not after a day, immediately. The problem begins with pressure. On Earth, the entire atmosphere presses gently against your body. You do not notice it because you have lived inside it every second of your life. The air around you is pushing inward, and the fluids and gases inside your body are pushing outward, and those forces are balanced. Your lungs, blood, tissues, eyes, and skin all expect that pressure. Mars has an atmosphere, but it is almost nothing compared with Earth's. It is thin enough that the surface pressure is only a tiny fraction of what your body is designed for. It is so thin that even though Mars has a sky and clouds and winds, it is closer to a vacuum than to the air you are breathing now. This means that if you tried to breathe on Mars, there would not be enough pressure to move oxygen into your bloodstream properly. But that problem almost does not matter, because there is essentially no breathable oxygen there anyway. The atmosphere is mostly carbon dioxide, with tiny amounts of nitrogen, argon, and trace gases. It is not air. It only looks like an atmosphere from a distance. Your first instinct would be to inhale, but your lungs would find almost nothing useful. You could not take a satisfying breath. You could not simply hold your breath either, because in low-pressure environments, holding your breath can be dangerous. The gas inside your lungs wants to expand. If pressure around you drops too quickly and you keep your airway closed, your lungs can be injured. In real vacuum survival training, the instruction is often to exhale because the body is better off letting expanding gas escape than trapping it. Mars is not a perfect vacuum, but for a human body, it is still dangerously low pressure. Then there is a phenomenon called ebullition. At low enough pressure, water can begin to boil at body temperature. This does not mean your blood would boil like water in a kettle, because your circulatory system is pressurized by your body, but exposed moisture would behave strangely. The moisture on your tongue, in your eyes, and in your airways could begin to evaporate rapidly. Your tissues could swell. You would lose consciousness quickly from lack of oxygen. The exact time depends on the circumstances, but we are talking about seconds to perhaps a minute or two, not a heroic stroll across the landscape. And then the cold would begin to matter. Mars can be extremely cold, especially at night, at the poles, and in winter. But cold does not kill instantly in a near vacuum, because there is so little air to conduct heat away from you. That is one of the strange things about Mars. You could be standing in a place with a temperature far below freezing, but because the atmosphere is so thin, you would not feel wind chill the way you do on Earth. You would lose heat mainly by radiation and by contact with the ground. That is slower than being plunged into freezing water, but it does not save you because oxygen and pressure have already become fatal. So the first answer is simple. An unprotected human cannot survive on Mars at all, not for a meaningful amount of time. Mars is not a place where you can walk outside and adapt. It is not Antarctica. It is not a mountain. It is not a desert. It is a planetary environment outside the range of normal human biology. Every breath, every heartbeat, every exposed surface of the body would be depending on technology. And this is where the real story begins. Because when we ask whether humans can survive on Mars, we are not really asking whether our bodies can handle Mars. They cannot. We are asking whether our machines, habitats, life support systems, planning, discipline, and engineering can keep Mars away from us for long enough to live there. Mars would not need to attack us. It would only need one seal to fail. The most important thing to understand about living on Mars is that survival would not happen on the planet. It would happen inside a bubble. A habitat on Mars would be more like a spacecraft that happens to sit on the ground than like a normal house. It would need pressure, oxygen, temperature control, radiation shielding, water recycling, air filtering, fire safety, power systems, communication systems, dust protection, and emergency backups. A person inside that habitat would not truly be living in the Martian environment. They would be living in a carefully maintained artificial slice of Earth, surrounded on every side by a world that cannot support them. Pressure is the first layer of that bubble. Human beings need a pressurized environment because our lungs evolved for Earth. At sea level, Earth's atmospheric pressure is about 1 bar. On Mars, surface pressure averages only around 6 to 7 millibars, less than 1% of Earth's sea level pressure. That is lower than the pressure at the top of Mount Everest by an enormous margin. It is not just thin mountain air, it is a near vacuum. Any long-term human habitat would need to be sealed and pressurized, probably not all the way to sea level pressure, but high enough to keep people healthy and allow them to breathe safely. But the higher the internal pressure, the more force the habitat walls must resist. Every square meter of wall would have air pushing outward, trying to escape. That means a Mars habitat is not just a room, it is a pressure vessel. Every joint, window, hatch, pipe, and cable entry becomes a possible leak point. On Earth, a draft through a wall is annoying. On Mars, a leak is an emergency. If the leak is small, sensors might detect it and systems might compensate. If it is large, the habitat could depressurize quickly. The crew would have to isolate the damaged section, seal bulkheads, find emergency masks, and perhaps move into another module. This is why redundancy matters. A serious Mars base could not rely on one habitat, one oxygen generator, one power source, one water tank, one airlock, or one communications link. It would need layers of backups. It would need compartments that can be sealed off. It would need emergency shelters inside the larger habitat. It would need repair supplies, spare parts, and the ability to manufacture some components locally. Mars is too far away for rescue in the normal sense. If something breaks, the first response is not, "Call someone to come fix it." The first response is, "What do we already have here?" Temperature control is another layer. Mars is cold, but not in a simple way. The planet can have relatively mild temperatures near the equator during the day, but the nights can become brutally cold. The thin atmosphere does not store heat well. Sunlight warms the ground, but once the sun sets, heat escapes quickly into space. A habitat would need insulation and active heating. It would also need cooling, because humans, electronics, lights, machinery, and life support equipment all generate waste heat. In a sealed environment, heat does not just disappear. It has to be moved somewhere. On Earth, buildings dump heat into the surrounding air. On Mars, the air is too thin to make that easy. Radiators would likely be needed, just as spacecraft use radiators to release heat into space. That creates a strange situation. A Mars habitat might sit on a freezing planet and still need cooling systems to prevent certain parts from overheating. Survival is not only about staying warm, it is about controlling energy flow precisely. Then there is oxygen. A Mars base could bring oxygen from Earth, but carrying everything from Earth is expensive and limiting. The long-term dream is to make oxygen on Mars. The atmosphere is mostly carbon dioxide, and carbon dioxide contains oxygen atoms. In principle, machines can split those atoms away and produce breathable oxygen or oxygen for rocket propellant. NASA's MOXIE experiment on the Perseverance rover was a small demonstration of this idea. It did not produce enough oxygen for a crew, but it proved that oxygen could be extracted from the Martian atmosphere under real Martian conditions. A full-scale system would have to be much larger, more reliable, and able to run for months or years. It would have to produce oxygen not only for people to breathe, but possibly for the return rocket. This is critical because rockets do not only need fuel, they need oxidizer. On Earth, rockets carry oxygen because space has no air. A rocket leaving Mars would also need oxidizer. Producing oxygen on Mars could reduce the amount of material that must be launched from Earth, but it also creates a dependency. If the oxygen plant fails, the mission changes from exploration to survival. Water is just as important. Humans need it to drink, grow food, produce oxygen, maintain hygiene, regulate temperature, and support chemistry. Mars does have water, but mostly as ice, locked in the ground, concentrated in polar regions, buried beneath dust, or mixed with salts. A crew would need to choose a landing site partly based on accessible water ice. Too far from water, and the settlement becomes dependent on imports. Too close to the poles, and sunlight, temperatures, and operations become harder. Every site is a trade-off. So the first real requirement for surviving on Mars is not courage, it is infrastructure. Without infrastructure, Mars kills quickly. With enough infrastructure, Mars becomes possible. But the more carefully you list what is required, the more obvious it becomes that Mars survival is not one invention. It is an entire world of machines working together, without pause, in an environment that does not forgive mistakes. One of the most dangerous things about Mars is that it almost looks familiar. In photographs, you see rocks, hills, plains, dust, clouds, shadows, sunrise, sunset. You see a horizon. you see a landscape. Your brain wants to treat it like a remote place on Earth, a desert in another color, a silent wasteland, maybe, but still a place. That illusion is powerful and dangerous because the most important threats on Mars are not always visible. The atmosphere is a good example. Mars has weather, it has wind, it has dust devils, it has clouds, it has seasonal changes. Sometimes the entire planet can be affected by dust storms. From orbit, Mars can look like a world with a living sky. But standing on the ground, that sky would not protect you the way Earth's atmosphere does. Earth's atmosphere is not just something we breathe. It is a shield, a blanket, and a stabilizer. It blocks much of the sun's harmful ultraviolet radiation. It burns up many small meteoroids before they hit the ground. It spreads heat around the planet. It gives water enough pressure to remain liquid at the surface. It supports weather systems that, despite their dangers, are part of a stable climate network. Mars has lost much of that. Its atmosphere is mostly carbon dioxide and extremely thin. It offers little protection from radiation. It does not keep the surface warm. It cannot support liquid water for long at ordinary surface conditions. The result is a world that has some of the visual features of Earth, but not the life-supporting functions of Earth. The pressure problem also affects water in a strange way. On Earth, water can sit in a lake, flow in a river, fall as rain, or fill a glass. On Mars, if you poured pure liquid water onto the surface, it would not behave normally for long. Depending on temperature and pressure, it would tend to freeze, evaporate, or boil away. Salty brines might exist temporarily under certain conditions, but stable rivers and lakes are not part of modern Mars. This matters because human settlements are often imagined beside water sources, but on Mars, water is not waiting as lakes under a blue sky. It is a resource hidden in ice, minerals, buried layers, and difficult chemistry. The thin atmosphere also changes sound. Sound needs matter to travel through, and Mars has so little air that sounds would be quieter and altered compared with Earth. A human voice outside would not carry normally, even if you could speak, which you could not without a suit. The landscape might look open, but it would feel acoustically dead. Machines would hum inside pressure shells. Footsteps would transmit through suit structure more than through the air. The world outside would be a red silence. Then there is dust. Martian dust is not just ordinary dirt. It is extremely fine, dry, and electrostatically clingy. It can coat solar panels, clog mechanisms, scratch surfaces, contaminate seals, and enter airlocks. Lunar dust was a major annoyance for Apollo astronauts, and Mars dust would be a long-term operational problem. It would get onto suits, tools, rovers, solar arrays, radiators, windows, filters, and machinery. Every time astronauts return from an EVA, from an outside walk, dust comes with them, unless the system is designed to keep it out. This is why suit ports are often discussed for Mars missions. Instead of bringing the entire dusty spacesuit inside the habitat, a suit port lets the suit attach to the outside of the habitat. The astronaut climbs in and out through a rear hatch, leaving most of the dust outside. It sounds like a small design detail, but on Mars, small details become survival systems. Dust in the wrong place could degrade equipment slowly until a seal fails, a filter clogs, or a hinge jams. Mars dust may also contain reactive chemicals, including perchlorates in the soil. Perchlorates are salts that can interfere with human thyroid function and can complicate agriculture. They are not necessarily impossible to manage, but they mean Martian soil is not simply dirt waiting for seeds. You cannot just scoop it into a greenhouse and grow potatoes without treatment. The soil would need processing, washing, chemical management, microbial systems, or imported growth media. A Mars farm would be a controlled life support system, not a garden in the ground. The atmosphere creates another problem for landing. It is thick enough to cause dangerous heating when spacecraft enter, but too thin to slow heavy vehicles easily with parachutes alone. Earth has a thick atmosphere that helps spacecraft brake. The Moon has no atmosphere, so landers use rockets from the start. Mars sits in an awkward middle. You hit the atmosphere fast enough to need a heat shield, but then the air is too thin to do all the slowing. This makes landing large human-class payloads very difficult. Getting people to Mars is hard, but getting massive habitats, supplies, ascent vehicles, power systems, and equipment safely onto the surface may be one of the hardest parts. And once those systems land, they must keep working in dust, cold, radiation, and low pressure. This is why Mars is terrifying in a quiet way. It does not look like a place of fire or storms all the time. It often looks still, almost peaceful. But that stillness is not safety. It is the stillness of a world where nothing is trying to keep you alive. Radiation may be the most invisible threat on Mars. On Earth, we live beneath layers of protection. Above us is the atmosphere, a thick ocean of gas that absorbs and scatters dangerous particles and radiation. Around us is Earth's magnetic field, which helps deflect charged particles from the sun and from deeper space. We rarely think about these shields because they are always there. They are part of the background of being alive. Mars does not offer that same protection. It has no global magnetic field today, and its atmosphere is too thin to block radiation the way Earth's does. There are two major radiation concerns for humans on Mars. The first is galactic cosmic rays. These are high-energy particles that come from outside the solar system, accelerated by extreme events like supernova explosions and other energetic astrophysical processes. They are difficult to shield against because some of them are extremely energetic. They can pass through spacecraft walls, habitat materials, and human tissue. When they strike atoms in shielding, they can sometimes create secondary particles, making shielding design complicated. You do not solve cosmic rays by simply adding a thin metal wall. The second concern is solar particle events. These are bursts of energetic particles from the sun, often associated with solar flares and coronal mass ejections. A major solar storm can send dangerous radiation through interplanetary space. On Earth, the atmosphere and magnetic field protect us. On Mars, an astronaut on the surface would need to take shelter. A habitat would need a storm shelter with extra shielding, perhaps surrounded by water tanks, food stores, regolith, or other materials rich in hydrogen, which can be useful for slowing certain particles. Radiation is not always dramatic in the moment. That is part of what makes it dangerous. A person might not feel cosmic rays passing through their body. They might not collapse immediately. But over time, radiation can damage DNA, increase cancer risk, affect the central nervous system, damage tissues, and threaten reproductive health. A Mars mission would involve exposure during the trip there, exposure on the surface, and exposure during the trip home. The total dose matters. This creates a strange design problem. A Mars settlement needs shielding, but shielding is heavy. Launching heavy material from Earth is expensive. So one obvious solution is to use Mars itself. Cover habitats with Martian regolith, build underground, place modules inside lava tubes, use buried shelters, surround sleeping areas with water tanks or supply walls. Let the planet become part of the shield. this is not just about comfort. It may be necessary for long-term health. The idea of living underground on Mars may sound disappointing because science fiction often imagines glass domes under the stars. But glass domes are probably one of the least realistic early settlement concepts. Transparent structures are difficult to pressurize, hard to shield, vulnerable to impacts, and poor at blocking radiation unless made extremely thick or complex. A real early Mars base might look less like a shining city and more like a cluster of buried cylinders, covered modules, tunnels, shielded shelters, and machinery half sunk into the soil. That is not as romantic, but it is more honest. The safest Mars habitat may be one that hides. Radiation also affects electronics. Spacecraft computers, sensors, power systems, and communication devices need radiation-hardened components or protective design. A bit flip in a computer memory cell might sound minor, but in a life support system, navigation system, or airlock controller, errors matter. Redundancy, error correction, shielding, and fail-safe design become essential. The machines keeping humans alive need to survive Mars too. Then there is ultraviolet radiation. Mars lacks an ozone layer like Earth's. Ultraviolet light can break down organic molecules and affect exposed materials. It can degrade plastics, fabrics, seals, and biological samples. It can also influence chemistry in the soil. A person outside in a suit would be protected by suit materials, but equipment left exposed for long periods would need UV-resistant design. Greenhouses would need materials that let in useful light while blocking harmful radiation and maintaining pressure. Again, nothing is simple. Radiation changes the psychology of Mars as well. On Earth, going outside is a relief. You open a door and step into the world. On Mars, outside is exposure. Outside is a suit. Outside is a checklist. Outside is limited time. Outside is radiation, dust, low pressure, and the constant awareness that your survival depends on a layer of material between your body and the planet. Even if astronauts become used to it, the relationship with the outdoors would be fundamentally different. A Mars settlement would therefore have to be designed not only to protect bodies, but also to protect minds. If people live underground or inside shielded modules for months or years, they need light, space, routine, privacy, beauty, exercise, social structure, and purpose. Radiation forces architecture inward. Human psychology pushes back, asking for windows, views, gardens, open areas, and natural rhythms. Some designs might use cameras and screens to create virtual windows. Others might build shielded viewing areas with thick, transparent materials. Some habitats might use fiber optic systems or mirrors to bring sunlight inside without exposing people directly. Future settlements might create underground atriums with artificial skies. These ideas sound aesthetic, but on Mars, aesthetics become survival too. A crew that loses morale is a crew in danger. So radiation is not just one hazard on a checklist. It shapes where we live, how we build, how we move, how long we stay, how we sleep, how we farm, and how much of Mars we can ever truly experience with our own eyes. Mars may be a planet, but to humans, without shielding, it is also a slow rain of invisible damage. Temperature on Mars is another problem that sounds simple until you look at it closely. People often say Mars is cold, and that is true. But Mars is not cold in the same way a winter night on Earth is cold. On Earth, cold air surrounds your body, conducts heat away, and moves across your skin. Water in the air can freeze. Wind can strip heat from you rapidly. On Mars, the atmosphere is so thin that the air itself carries much less heat. A cold Martian wind would not feel like a cold Earth wind of the same temperature, because there are far fewer molecules hitting you. But the ground, the sky, your equipment, your suit, and your habitat still lose heat. The cold is real, it just behaves differently. Mars has huge temperature swings. Near the equator, daytime temperatures can sometimes rise to conditions that sound almost comfortable. But at night, the temperature can fall far below freezing. At higher latitudes or during winter, it can become brutally cold. The thin atmosphere cannot hold heat effectively, so the planet cools quickly after sunset. This means a Mars base would need to handle constant thermal cycling. Materials expand when warm and contract when cold. Seals, joints, cables, panels, windows, and mechanical parts would be stressed over and over again. Thermal cycling matters because Mars missions must last. A rover can be designed for a limited lifetime, and many rovers have heroically exceeded expectations. But a human base cannot be treated as a temporary science instrument. It has to be maintainable. It has to survive seasons. It has to endure dust storms, cold nights, warm days, and years of operation. Every material choice matters. Metals, plastics, composites, lubricants, batteries, hoses, valves, and electronics all behave differently under low pressure and low temperature. Batteries are especially important. Cold reduces battery performance. Rovers and habitats need power storage for night, emergencies, and dust storms. If batteries get too cold, they can lose capacity or fail. This is why thermal control is tied directly to power. You need power to keep systems warm, but you need warm systems to store and deliver power efficiently. A failure in one system can cascade into another. Solar power on Mars is possible, but complicated. Mars is farther from the sun than Earth, so it receives less sunlight. Dust in the atmosphere and dust settling on panels reduce output. Planet-wide dust storms can darken the sky for weeks. During such storms, solar-powered systems may struggle. NASA's Opportunity rover was eventually lost after a global dust storm blocked sunlight from reaching its solar panels. Human missions would need more robust power, likely combining solar with nuclear systems, energy storage, and careful load management. Nuclear power has major advantages on Mars. It can run day and night during storms, in winter, and at higher latitudes. Small fission reactors could provide steady electricity and heat. That heat itself is valuable. Waste heat that would be a nuisance in some environments becomes a resource on Mars. It can help keep habitats warm, prevent water systems from freezing, and support industrial processes. But nuclear power also brings mass, complexity, safety concerns, and deployment challenges. Reactors must be landed safely, placed far enough from habitats, shielded properly, and maintained or designed to operate for long periods with minimal human intervention. A Mars base cannot afford casual energy. Power is life. Without power, oxygen production stops, heaters stop, pumps stop, communications fail, water processing halts, food systems shut down, and the habitat begins moving toward the outside environment. This is why early Mars missions would likely be conservative. Before humans arrive, cargo missions might land power systems, habitats, supplies, rovers, and oxygen production equipment. Robots might test the systems for months or years. A crew might not depart Earth until the return vehicle is fueled, or at least verified. The romantic version is astronauts stepping onto Mars and building a future. The realistic version is infrastructure arriving first, quietly proving that it can keep humans alive before humans risk the journey. Temperature also affects spacesuits. A Mars suit must keep the astronaut warm in cold conditions. prevent overheating during exertion, maintain pressure, provide oxygen, remove carbon dioxide, resist dust, allow mobility, protect against radiation to some degree, and survive repeated use. That is difficult. A suit is not clothing. It is a tiny spacecraft shaped like a human body. If a glove becomes too stiff in the cold, dexterity suffers. If a joint seal collects dust, mobility suffers. If thermal control fails, the astronaut can overheat or freeze, even while surrounded by cold. Inside the habitat, temperature control becomes a human comfort issue as well. People need stable, livable conditions. Too cold, and they cannot rest, heal, work, or think clearly. Too hot, and the sealed environment becomes exhausting and dangerous. Humidity must be controlled. Condensation can lead to mold, corrosion, or electrical problems. Air circulation must prevent stagnant pockets. On Earth, a bad building is uncomfortable. On Mars, a bad building threatens the mission. Mars cold also shapes the search for water. Ice is useful, but frozen water must be extracted, melted, purified, stored, and protected from refreezing. Pipes must be heated or buried. Tanks must be insulated. Wastewater must be recycled. Every kilogram of water is precious. Even water used for radiation shielding may have to remain part of the life support inventory. So, when someone asks whether humans can survive the cold on Mars, the answer is yes, with enough engineering. But that answer hides the real difficulty. Mars is not just cold. It is variable, dry, dusty, low pressure, and far away. The cold is not one enemy. It is a background condition that makes every other system harder. A Mars habitat would be a warm room inside a freezer that is also a vacuum chamber, a radiation field, a dust storm environment, and a desert. And that warm room would have to keep working for years. Water is the difference between a visit and a settlement. A short mission can bring water from Earth, recycle it carefully, and treat it as a limited supply. A long-term settlement cannot depend entirely on water launched across interplanetary space. Water is too important, too heavy, and too useful. It is not just something to drink. It is oxygen, hydrogen, radiation shielding, agriculture, hygiene, chemistry, cooling, emergency reserve, and rocket propellant potential. If humans ever truly live on Mars, they will need Martian water. Mars does have water. This is one of the reasons Mars is so tempting. It is not a completely dry rock. We see evidence that ancient Mars had rivers, lakes, deltas, floods, and perhaps long-standing bodies of water. Today, most accessible water is frozen, trapped as ice in polar caps, buried in the subsurface, or mixed into minerals. Some locations have shallow ground ice. Others may have deeper reservoirs. The challenge is not whether water exists, but where it exists, how pure it is, how deep it is, and whether humans can reach it safely. A landing site for a human mission would likely be chosen partly for water access. This creates difficult trade-offs. The equator has better sunlight and milder temperatures, but easy water ice may be less available. Higher latitudes may offer more accessible ice, but colder conditions, lower sun angles, and harsher seasons complicate operations. A site near mid-latitude ice might be a compromise, but every compromise affects mission architecture. Extracting water from ice sounds straightforward. Dig it up, heat it, collect the vapor or melt water, filter it, and store it. But on Mars, each step is hard. Excavation equipment must work in low pressure, cold, dust, and partial gravity. Heating requires energy. The ice may be mixed with soil, salts, and chemicals. Purification systems must remove contaminants. The machinery must operate repeatedly without easy replacement parts. If the water processing plant fails, the settlement becomes dependent on stored reserves. Water recycling would be essential. The International Space Station already recycles water from humidity, urine, and other sources. A Mars habitat would need similar or more advanced systems. Every breath adds moisture to the air. Every shower, if showers are allowed, uses water. Every plant transpires water. Every system leaks a little. Closed-loop life support is not optional. The goal would be to lose as little as possible, but no recycling system is perfect. Filters clog, membranes degrade, pumps fail, microbes grow, sensors drift, chemicals build up. Humans are messy biological systems, and habitats are complex ecological machines, whether we admit it or not. A Mars base would need constant water monitoring. The water must be safe, balanced, and available. On Earth, municipal systems hide this complexity. On Mars, the crew lives inside the system. Oxygen is closely connected to water, but Mars offers another path. Because the atmosphere is mostly carbon dioxide, oxygen can be produced by splitting CO2. This is what MOXIE demonstrated at a small scale. The reaction takes carbon dioxide and separates oxygen, leaving carbon monoxide as a byproduct. For a human mission, oxygen production could support breathing, but the bigger demand may be rocket propellant. A return vehicle might need many tons of oxygen. Producing that oxygen locally could dramatically reduce the mass launched from Earth. However, producing oxygen for a crew and producing oxygen for a rocket are different scales. Breathing oxygen is measured in kilograms over time. Rocket oxidizer is measured in tons. A full-scale system would need power, compressors, heat, storage tanks, liquefaction, and reliability. It might run for months before the crew arrives, filling tanks slowly. Mission planners might require proof that enough oxygen exists for the return trip before humans even launch from Earth. That would be one of the most important safety checks in the history of exploration. Food is the next challenge. Early missions will bring most or all food from Earth. Stored food is reliable, but it degrades over time, takes mass and volume, and does not provide the psychological benefits of fresh crops. Long-term habitation requires agriculture, but Mars agriculture is not planting seeds outside. It is growing plants inside sealed, pressurized, temperature-controlled, radiation-shielded greenhouses with artificial or filtered light, recycled water, managed nutrients, and protected roots. Plants need carbon dioxide, water, light, nutrients, and suitable temperatures. Mars has carbon dioxide, but at low pressure and outside human-compatible conditions. The soil contains minerals, but also problems like perchlorates and lack of organic matter. Plants need nitrogen, phosphorus, potassium, trace elements, and biological support. Earth soil is alive. It contains microbes, fungi, organic material, structure, and chemistry built over millions of years. Martian regolith is not alive. To grow crops, humans would likely use hydroponics, aeroponics, treated regolith, composted waste, or engineered growth media. Food production becomes part of life support. Plants can absorb carbon dioxide and release oxygen. They can recycle nutrients. They can provide fresh food and psychological comfort. A small green leaf inside a Mars habitat would be more than calories. It would be evidence that Earth processes can survive somewhere else. But crops also introduce risk. Mold, pests, nutrient imbalance, crop failure, power outages, and disease can threaten food supplies. A settlement must store backup food even while growing more. Waste recycling becomes unavoidable. Human waste contains water, carbon, nitrogen, phosphorus, and other nutrients. On Earth, waste is often treated as something to remove. On Mars, waste is resource. but recycling waste safely into agriculture requires careful biological and chemical systems. Pathogens must be controlled, odors must be managed, nutrients must be balanced. Again, the settlement becomes an ecosystem. This is one of the deepest truths about Mars. You cannot live there by bringing only machines, and you cannot live there by bringing only biology. You need both. Machines create the conditions. Biology closes the loops. Humans sit in the middle, depending on pumps, filters, bacteria, plants, sensors, heaters, and chemistry. A Mars settlement is not a house on another planet. It is a living machine, and if the machine stops living, the humans do too. The human body itself is a Mars problem. We tend to imagine survival as an outside challenge: oxygen, water, radiation, temperature, food. But even if every external system works, the body has to endure months in space, years in partial gravity, isolation, altered sleep cycles, limited medical care, and an environment unlike anything in human evolutionary history. The journey to Mars alone is difficult. Depending on mission design, a crew might spend around 6 to 9 months traveling through interplanetary space. During that time, they live in microgravity unless the spacecraft has artificial gravity, which no crewed deep space vehicle currently uses at that scale. In microgravity, the body changes. Muscles weaken because they do not work against weight. Bones lose density because the skeleton is not loaded normally. Fluids shift toward the head. Vision can be affected. The cardiovascular system adapts. Balance systems change. Astronauts on the International Space Station exercise for hours every day to reduce these effects, but they do not eliminate them completely. Mars has gravity, but only about 38% of Earth's. That is better than microgravity, but we do not know whether it is enough for long-term human health. No human has lived for years in Martian gravity. We do not know how bones, muscles, blood circulation, pregnancy, child development, immune function, or aging would behave over decades at 0.38 g. This is one of the biggest unknowns. Mars might be enough to keep people mostly healthy with exercise, or it might cause slow problems we cannot yet predict. If Mars gravity is not enough, settlements might need artificial gravity habitats, rotating sleeping quarters, centrifuges for exercise, or medical countermeasures. But all of those add complexity. The simplest vision of Mars colonists living normally under the red sky skips a huge biological question. Humans are Earth animals. Every cell in our body evolved under one gravity. Mars is asking whether that can be negotiated. Medical care is another major issue. On Earth, a serious injury or illness can be treated by hospitals, specialists, scans, surgeries, blood supplies, pharmacies, and emergency transport. On Mars, the crew has what they brought, what they can make, and the medical skills of the people present. A broken bone, appendicitis, kidney stone, infection, dental emergency, allergic reaction, or mental health crisis becomes far more serious when Earth is months away. Telemedicine helps, but communication delay makes real-time guidance impossible. Depending on the positions of Earth and Mars, one-way radio signals can take several minutes to over 20 minutes. A conversation with doctors on Earth becomes a slow exchange, not a live call. This means a Mars crew must include medical expertise and medical equipment. They may need surgical capability, imaging tools, sterilization, pharmaceuticals, dental tools, rehabilitation equipment, and training across the crew. But mass is limited. You cannot bring a full hospital. You bring a carefully chosen medical system and hope the emergencies match your preparations. Psychology may be just as important as medicine. A Mars crew lives in confinement, isolation, danger, and delay. They cannot step outside without preparation. They cannot go home quickly. They cannot receive immediate help. They see the same small group of people every day. They live with constant background risk. Even if everyone is highly trained and emotionally stable, conflict, loneliness, stress, boredom, grief, sleep disruption, and homesickness are real hazards. The sky itself may affect them. Earth is not just a place. It is the entire human context. Weather, oceans, forests, crowds, smells, birds, rain, cities, family, open doors, random walks, fresh air. On Mars, all of that is gone. Earth becomes a bright point in the sky at certain times, a place that can be seen but not reached. For early crews, that emotional fact may be profound. They would be farther from home than any human beings in history. The habitat would need to support mental health intentionally. Private spaces, shared spaces, exercise areas, good lighting, plants, music, communication routines, meaningful work, recreation, maybe virtual reality environments, maybe windows, even if shielded or indirect, maybe rituals that mark time. Mars has a day length close to Earth's, about 24 hours and 39 minutes, which helps. But the year is much longer, about 687 Earth days. Seasons move differently. The sun appears smaller. The night sky is familiar, yet alien. Time itself becomes strange. Sleep is also important. Life support systems make noise. Crews work shifts. Dust storms dim sunlight. Communication schedules depend on Earth. Stress affects rest. Poor sleep reduces judgment, emotional control, immune function, and performance. In a dangerous environment, fatigue can be deadly. The calm image of astronauts gazing out at Mars hides a daily reality of schedules, checklists, maintenance, exercise, monitoring, and disciplined routine. Then there is reproduction. Could humans have children on Mars? We do not know. This is one of the most sensitive and uncertain questions. Radiation, reduced gravity, medical limitations, developmental biology, ethics, and settlement stability all matter. A true civilization on Mars would eventually require families, children, education, culture, and generations. But early Mars bases are not likely to be places for childbirth. They will be research outposts and engineering settlements first. The leap from surviving on Mars to being born on Mars is enormous. So, when people ask whether humans can survive on Mars, they often imagine oxygen tanks and domes. But survival also means bones, blood, immune systems, eyes, sleep, relationships, grief, boredom, hope, and identity. A Mars settlement must keep the human body alive and the human mind willing to continue. The planet challenges our engineering. The distance challenges our courage. But the years challenge our humanity. To understand what survival would feel like, imagine one ordinary day at an early Mars base. The crew wakes not to birds, traffic, rain, or wind through trees, but to the controlled rhythm of machines. Air circulation fans, pumps, quiet alarms, temperature sensors, carbon dioxide scrubbers. The soft background sound of a habitat refusing to become Mars. The first thing the crew does may not be looking out a window. It may be checking the numbers, oxygen partial pressure, carbon dioxide levels, humidity, water reserves, battery charge, reactor output, solar forecast, radiation alerts, suit status, rover status, dust forecast, communication queue from Earth. On Earth, most people wake up inside a world that already works. On Mars, the world works only because the base worked all night. Breakfast might be simple. Rehydrated food, stored grains, maybe fresh greens if the greenhouse is productive. Coffee or tea made from recycled water. Every meal is part of inventory. every package becomes waste to process. Every crumb matters more than it would on Earth, not because people are starving, but because closed systems teach respect. Nothing simply disappears. The settlement must account for what enters, what leaves, and what cycles. Then comes exercise, not optional, not a hobby, a medical requirement. In reduced gravity, muscles and bones need stress. Crews may use resistive machines, treadmills with harnesses, cycling systems, and maybe centrifuge sessions if future habitats include them. Exercise takes time, but skipping it risks long-term weakness. A person on Mars must remain strong enough to work, repair, climb, lift, and respond to emergencies. Fitness becomes part of life support. After that, the day divides into maintenance, science, construction, farming, and operations. Maintenance may dominate, replacing filters, inspecting seals, cleaning dust traps, testing backup valves, checking water processors, reviewing airlock cycles, updating software, lubricating rover parts, examining suit joints, measuring greenhouse chemistry. The glamorous image of Mars exploration often hides this truth. A huge portion of life there would be keeping the base alive. If an EVA is planned, preparation begins early. The crew reviews the route, goals, hazards, timeline, communication plan, emergency return options, suit consumables, weather, and radiation conditions. They inspect each other's suits. They check oxygen, carbon dioxide removal, battery capacity, cooling systems, radio links, tools, sample containers, and dust seals. Then they enter the airlock or suit port system. The transition from inside to outside is not casual. It is a ritual because rituals reduce mistakes. Outside, Mars may be stunning. A pale salmon sky, red-brown rocks, distant hills softened by dust, the sun smaller than on Earth, shadows sharp in thin air, the landscape almost silent, every footstep slower under reduced gravity, every movement shaped by the suit. The astronauts may collect rocks, deploy instruments, inspect equipment, repair a cable, clean a solar array, or scout a construction site. But time outside is limited. Oxygen, battery power, carbon dioxide capacity, radiation exposure, fatigue, and dust all set boundaries. A small problem outside can grow quickly. A warning light, a pressure drop, a glove abrasion, a cooling issue, a rover fault, a dust storm building on the horizon. The crew must decide whether to continue or return. On Earth, people often push through minor issues. On Mars, discipline means turning back early. Survival favors caution over pride. Back inside, the crew does not simply remove helmets and relax. Dust control begins. Suits are cleaned or left outside through suit ports. Samples are contained. Air quality is checked. Equipment is logged. The crew may undergo medical checks. Data is transmitted to Earth. The mission team sends delayed feedback. Scientists on Earth may be thrilled by a rock the crew found hours ago, but the crew has already moved on to repairs, food, exercise, and planning. In the greenhouse, another kind of work continues. Plants are inspected for stress, discoloration, pests, fungal growth, nutrient problems, water imbalance, and light exposure. A plant disease that would be annoying in an Earth garden could threaten fresh food production in a closed Mars habitat. The greenhouse is both farm and biosensor. If plants are healthy, part of the base is healthy. If plants fail, something in the system may be wrong. Evening may bring messages from Earth. Video clips from family, mission updates, news summaries, scientific responses, jokes, music, maybe recordings from children or friends. But the delay changes intimacy. You cannot interrupt. You cannot share a live laugh. you send pieces of yourself across space and receive pieces back later. The crew learns a slower form of connection. Then the habitat enters night mode. Lights shift, power use changes. Some systems run quieter. The outside temperature falls. Frost may form in certain areas. Dust settles or moves. The sky darkens over a planet where no human can stand unprotected. Inside, someone may look at Earth if it is visible, not as a place on a map, but as a bright point containing everyone they love. This ordinary day may sound controlled, even peaceful, and perhaps many days on Mars would be like that. Not constant crisis, not dramatic explosions, just routine inside danger. That is how extreme environments are survived. Not by panic, but by habits. Not by hero speeches, but by checklists. Not by pretending the danger is gone, but by respecting it every morning. A Mars base would succeed when its crew can have boring days. Because on Mars, boredom would be a victory. Now imagine the same base during an emergency, not a catastrophic movie disaster, something smaller, something realistic. A pressure sensor detects a slow leak in one module. At first, nobody hears anything. There is no dramatic rushing wind, no objects flying across the room, just a number changing on a screen. The system flags it. The crew checks whether it is a sensor fault. Another sensor agrees. The pressure is dropping slowly. Immediately, the base changes personality. Conversations become shorter. Checklists open. Non-essential activities stop. The crew isolates sections, closing internal hatches to narrow the leak location. The life support system increases output to compensate, but only within limits. Every liter of gas matters. The crew checks recent maintenance logs. Which panel was opened? Which airlock cycled? Which rover docking port was used? Which pipe could be leaking? The answer may be hidden behind a wall, under equipment, or near a seal dust has slowly damaged. If the leak is found, it must be patched. Maybe with a sealant kit, maybe with a clamp, maybe with a replaceable gasket, maybe with a temporary plate. The repair must hold under pressure. It must not contaminate the air. It must be inspected later. If the leak is not found quickly, the crew may abandon that module temporarily, leaving it depressurized until a safer repair plan exists. On Earth, this would be a building maintenance problem. On Mars, it is a reminder that every wall is part of your lungs. Another emergency might be power loss. A dust storm reduces solar output more than expected, while a battery string underperforms. The base begins load shedding. Science instruments shut down. Some greenhouse lights dim. Non-essential heating reduces. Rovers stop charging. The crew moves into energy conservation mode. If a nuclear reactor is present, perhaps the situation is manageable. If not, the crew must decide how to ration power while protecting life support, water systems, and thermal control. Power emergencies are dangerous because they can cascade. Less power means less heat. Less heat means colder batteries. Colder batteries perform worse. Pumps may slow. Water lines may freeze. Electronics may drop below safe temperatures. A system designed with enough margin can ride through the storm. A system with poor margin becomes a chain reaction. A medical emergency is even more personal. Suppose an astronaut develops severe abdominal pain. Is it kidney stone, appendicitis, infection, food issue, stress? On Earth, imaging, labs, specialists, and surgery may be available quickly. On Mars, the crew doctor may be the only doctor on the planet. Earth can advise, but delayed. The crew may need to use ultrasound, blood tests, limited medications, and decision trees. If surgery is needed, the habitat becomes an operating room. Every medical event is harder because evacuation is impossible. Fire may be the most feared habitat emergency. Smoke in a sealed environment is immediately serious. The crew must locate the source, isolate power, suppress flames, protect breathing, and prevent toxic gases from spreading. Fire suppression systems must work without making the atmosphere unbreathable. Afterward, smoke particles, damaged materials, and chemical residues must be cleaned from the air. A small electrical fire could leave lasting contamination if not controlled. Then there is the nightmare of an EVA emergency. An astronaut outside notices suit pressure dropping. The suit alarm sounds. The nearest airlock is hundreds of meters away. The rover is nearby, but not close enough. The astronaut must move carefully because panic increases oxygen use and risks falls. A teammate may assist. The base may prepare emergency repressurization. The difference between survival and death may be a patch kit, training, distance, and calm. This is why simulations matter. Crews must practice emergencies until responses become automatic. Not because they expect disaster every day, but because the first time cannot be the real time. Mars allows no casual learning curve. Emergency procedures must be tested on Earth, in analog habitats, underwater, in deserts, in polar stations, and in space stations before Mars ever sees humans. Robots can help. A settlement might use inspection robots, repair drones, autonomous rovers, and internal monitoring systems. Robots can check external surfaces during storms, clean panels, inspect leaks, carry tools, scout terrain, and perform dangerous tasks. But robots can fail too. They need power, maintenance, software, spare parts, and human oversight. Automation reduces risk. It does not eliminate responsibility. The most important emergency resource may be culture. A crew that hides mistakes is doomed. A crew that blames people instead of fixing systems becomes dangerous. On Mars, near misses must be reported honestly. Small anomalies must be investigated. Maintenance must not be skipped because everyone is tired. Leaders must listen. Engineers must design for human error. The base must assume that people will sometimes forget, misread, rush, or misunderstand, and it must catch those mistakes before Mars does. This is one of the quiet truths of high-risk environments. Survival is not about never making mistakes. Humans always make mistakes. Survival is about building systems that keep mistakes from becoming fatal. Mars will test that constantly, not with monsters, not with explosions every day, but with slow leaks, clogged filters, tired minds, dusty seals, weak batteries, delayed messages, and tiny choices that matter more than they should. There is also the question of how Mars changes over time around a settlement. The planet has seasons. Its axial tilt is similar to Earth's, so Mars experiences spring, summer, autumn, and winter, but its year is almost twice as long. Seasons are also affected by the planet's elliptical orbit. Dust activity changes with season. Carbon dioxide frost forms and sublimits at the poles. Atmospheric pressure shifts as CO2 freezes out and returns to the atmosphere. Temperatures rise and fall. Sunlight angles change. A settlement would not live in a static environment. It would live with a Martian calendar. The Martian day, called a sol, is about 39 minutes longer than an Earth day. This is close enough to feel familiar, but different enough to accumulate. Mission teams on Earth working on Mars rover time have experienced how strange it can be to shift by 39 minutes each day. For people living on Mars, the sol would become normal. Clocks would be slightly different. Work cycles would follow local sunrise and sunset, power demand, communications windows, and mission needs. A Mars calendar may become part of culture. Landing anniversaries, first harvest days, dust storm seasons, Solar conjunction periods, when the Sun interferes with communication between Earth and Mars. During solar conjunction, communication may be limited or paused for safety. Imagine a settlement accustomed to delayed messages from Earth suddenly becoming even more isolated for days or weeks. The silence would be expected, but still psychologically powerful. The landscape itself may change slowly. Dust accumulates. Tracks from rovers may persist. Landing sites may become industrial zones. Regolith moved for shielding forms berms and mounds. Habitats become partly buried. Roads or compacted paths appear. Solar arrays spread across plains. Radiators stand like dark wings. Antennas point toward Earth. The first base may look less like a city and more like a survival machine assembled across the dust. Over years, the settlement would create a human footprint. This raises environmental questions. Mars has no known ecosystems on the surface, but it does have geology, chemistry, and scientific integrity. Exhaust, leaks, waste, discarded hardware, and microbial contamination must be managed. Early exploration sites on the Moon are already treated as historic. Mars landing sites may become heritage locations too. The first human footprints on Mars may be preserved for a very long time in the thin, dry air. Dust storms could bury equipment or reveal it again. Fine dust may coat everything. Static charges may build. New research continues to reveal Mars as an active environment, not a dead museum. Dust devils move across plains. Frost appears and disappears. Slopes shift. Seasonal features change. Small meteorites strike the surface. Mars is quiet, but not frozen in time. A settlement must learn local weather, not just from orbit, but from lived experience. Which winds bring dust? Which seasons stress power? Where does frost form? Which rover routes become hazardous? Where does the ground hide ice? Which slopes are stable? Which materials degrade fastest? Over time, Martian settlers would develop practical knowledge no Earth-based mission plan can fully provide. This is true of every place humans have lived. Maps and models help, but local knowledge matters. On Mars, local knowledge might include how dust behaves near a particular ridge at sunset, how airlock seals perform after a storm, how greenhouse humidity changes during winter, how crew mood shifts during long communication gaps, how rover batteries behave on cold mornings, and which rocks are more abrasive to wheels. Eventually, Mars would produce experts who know Mars not only scientifically, but personally. People who can look at the sky color and anticipate dust. People who know the sound of a healthy pump versus a failing one. People who can navigate between habitats by landmarks under a dim sun. People who think in souls instead of days. People for whom Earth is origin, but Mars is routine. This is how a hostile place becomes a lived place. Not because it stops being hostile, but because humans learn its patterns. And yet Mars will always remain larger than the settlement. No matter how many habitats we build, most of the planet will remain empty. Enormous volcanoes, canyons, cratered highlands, frozen plains, polar caps, and buried histories stretch beyond any base. Even a thriving settlement would be a tiny dot on a vast world. That scale may be humbling. It may also be freeing. Mars offers room, silence, and time in ways Earth no longer does. But room is not the same as welcome. A desert can be vast and still kill you. Mars would give humanity space, but not mercy. The settlers would have to bring mercy with them, in their designs, in their rules, in the way they care for each other. The distance to Mars may be the most underrated danger. Mars is often called nearby, and in cosmic terms, it is. Compared with the stars, Mars is right next door. Light can travel from Earth to Mars in minutes. Spacecraft can reach it in months. We have sent orbiters, landers, rovers, and helicopters there. We have mapped it, measured it, photographed it, drilled into it, listened to its wind, and watched dust devils cross its plains. Mars is familiar compared with the rest of the universe, but for humans, Mars is very far away. The distance between Earth and Mars changes constantly as both planets orbit the Sun. Sometimes they are relatively close. Sometimes they are on opposite sides of the Sun, separated by hundreds of millions of kilometers. Mission planners use launch windows, which open roughly every 26 months when the geometry allows efficient travel. This means you cannot launch to Mars whenever you feel like it. You wait for the planets to align in a useful way. This affects rescue. On Earth, if something goes wrong in Antarctica, rescue may be difficult, but it is imaginable. If something goes wrong on the Moon, a rescue mission is still extremely hard. But the Moon is only about 3 days away with Apollo-style trajectories. Mars is months away, and launch windows matter. If a crew on Mars has a major problem, Earth cannot simply send help immediately and expect it to arrive next week. The crew must be self-reliant. Communication delay changes everything too. On the International Space Station, astronauts can speak with mission control almost instantly. On Mars, delay makes conversations asynchronous. If an astronaut asks a question, the answer may not arrive for many minutes, and then the reply to that answer takes many more. In an emergency, Earth can advise, but Mars must act. Mission control becomes less like a pilot in the loop and more like a distant support team writing delayed messages across the void. This means Mars crews need autonomy. They must be trained not only to follow procedures, but to diagnose, improvise, repair, and make decisions. They need authority to act without waiting for Earth. That changes the psychology of spaceflight. Apollo astronauts were far away, but still within real-time radio conversation. Mars astronauts would be the first crews to experience true operational independence from Earth. Supply delay is even more serious. Every spare part must be planned. Every tool must earn its mass. Every consumable must be tracked. If a pump fails and there is no replacement, the crew may need to rebuild it, print a component, cannibalize another system, or change mission operations. Additive manufacturing, like 3D printing, could help, but printers need feedstock, power, designs, and materials. You cannot print everything. Precision electronics, pressure seals, medical supplies, and complex mechanical parts may still need Earth manufacturing. This is why standardization matters. A Mars base should use modular components that can be swapped, repaired, and repurposed. It should avoid too many unique parts. It should have common connectors, common valves, common fasteners, common filters where possible. Engineers call this maintainability, but on Mars, it becomes survival architecture. A beautiful machine that cannot be repaired is a liability. The journey itself also exposes crews to danger. Launch from Earth is risky. Spaceflight is risky. Interplanetary cruise includes radiation, microgravity, equipment failures, navigation requirements, and possible solar storms. Then comes Mars entry, descent, and landing, one of the most challenging phases. The spacecraft must hit the atmosphere at high speed, survive heating, slow down, deploy systems, and land safely. Mars has already destroyed many robotic missions. Landing humans and heavy cargo will be harder. After landing, the crew must adapt to gravity again, but not Earth gravity. They may arrive deconditioned from months in space. They must check habitat systems, power, communication, supplies, rovers, suits, and return systems. The first days on Mars could be physically and mentally demanding. The crew may be excited, but they are also entering the highest risk surface phase. Returning is another challenge. A Mars mission must not only land humans, but launch them back from Mars, rendezvous perhaps with an orbital vehicle, and bring them home through interplanetary space and Earth re-entry. The Mars ascent vehicle must work after sitting on Mars for months or years. Its propellant must be stored or produced. Its systems must survive dust, cold, and radiation. A failure in the return vehicle could strand the crew. This is why some mission plans involve pre-positioning the return system before the crew arrives. The return vehicle might land first, produce oxygen from the atmosphere, verify its tanks are filled, and only then would astronauts launch from Earth. This approach feels cautious, but caution is what Mars demands. A mission that depends on something working later must prove it as early as possible. Distance also affects politics and funding. A human Mars program would require long-term commitment across years, perhaps decades. Governments change, budgets change, public attention changes, technical setbacks happen. A real settlement cannot be built on hype alone. It needs continuity, logistics, manufacturing, international agreements, planetary protection protocols, safety standards, and a reason to continue after the first footprints. And that raises a deeper question. Why go at all? Science is one answer. Mars preserves clues about early planetary habitability, water, climate change, and the possibility of past life. Human exploration could accelerate discovery. Long-term survival of civilization is another answer. A multi-planet species may be more resilient. Inspiration is another. Mars expands the human story, but none of these answers make the planet easier. Purpose helps people endure difficulty, but it does not remove the difficulty. Mars is close enough to tempt us, far enough to trap us. And that combination is why it occupies such a strange place in the human imagination. A spacesuit on Mars would be one of the most important machines ever built. It is easy to think of a spacesuit as clothing, but that is wrong. A Mars suit would be a spacecraft with arms and legs. It must create pressure around the body, provide oxygen, remove carbon dioxide, control temperature, protect from dust, resist abrasion, allow movement, carry communications, monitor health, and keep working after repeated use in an environment that wants to destroy it slowly. Pressure is the core problem. Traditional spacesuits are gas pressurized. They surround the astronaut with oxygen or a breathing mixture at low pressure. But gas pressure makes suits stiff. The higher the pressure, the harder it is to bend joints. Astronauts working outside the International Space Station often describe spacewalks as physically exhausting, partly because the suit resists movement. Mars astronauts would need to walk, climb, kneel, carry tools, repair equipment, collect samples, drive rovers, connect cables, and possibly respond to emergencies. Mobility matters. One idea is mechanical counterpressure suits. Instead of pressurizing the body with gas, a tight elastic garment applies pressure directly to the skin. This could allow greater mobility, at least in theory. The helmet and breathing system still need gas pressure, and sealing the suit around joints and body shapes is difficult. But Mars may push suit design beyond the bulky models we know today. A crew that works outside often needs suits that are durable, repairable, and less exhausting. Dust is the suit's enemy. Fine Martian dust could cling to fabric, scratch visors, infiltrate joints, damage seals, and contaminate the habitat. Every EVA becomes a dust management problem. Airlocks could include cleaning systems, brushes, electrostatic dust removal, vacuum systems, or suit ports. But dust always finds paths. The crew must treat dust as a long-term hazard, not just dirt. Suit gloves are especially difficult. Human hands are precise tools. Astronauts need to grip, turn, plug, repair, collect, and manipulate. Thick gloves reduce touch and dexterity. Cold stiffens materials. Pressure resists finger movement. Dust threatens seals. A small glove failure can become fatal. Designing gloves that are protective and usable is one of the hardest parts of spacesuit engineering. The helmet matters too. A Mars helmet must protect against low pressure, dust, impacts, ultraviolet radiation, and temperature changes while allowing visibility. Visors can scratch. Dust can coat them. Sun glare can blind. Condensation can form inside. Cameras, lights, heads-up displays, and communication systems may help, but all add complexity. An astronaut looking at Mars through a visor is seeing another planet through a life support machine. Rovers extend the suit's reach. A pressurized rover would allow astronauts to travel farther without staying in suits the entire time. Inside a rover, they could breathe normally, eat, rest, operate instruments, and perhaps sleep during multi-day traverses. But a rover is another habitat on wheels, with pressure, oxygen, power, thermal control, navigation, communication, and emergency systems. If it fails far from base, the crew must have a plan. Distance from habitat equals risk. Unpressurized rovers are simpler, but require suits the whole time. They may be useful near the base, but for serious exploration, pressurized mobility becomes valuable. Mars is a planet, not a landing site. The science will be spread across kilometers and eventually hundreds of kilometers. Ancient lake beds, lava flows, canyons, ice deposits, mineral layers, and possible caves are not all next to the habitat. Mobility determines discovery. Airlocks are another critical interface. An airlock is not just a door. It is a controlled transition between Earth-like pressure and Mars-like pressure. It must cycle air without wasting too much, prevent dust from entering, allow emergency access, fit suits and equipment, and survive repeated use. The more often astronauts go outside, the more important airlock efficiency becomes. Wasting oxygen and nitrogen every time would be costly. Systems might recover air before depressurization, storing it for reuse. Nitrogen is often overlooked. Humans breathe oxygen, but Earth's atmosphere is mostly nitrogen. Habitats may use nitrogen or another buffer gas to create a comfortable pressure and reduce fire risk. Mars has some nitrogen, but much less than Earth, and extracting it may be harder than extracting carbon dioxide. If nitrogen has to be imported, it becomes a precious resource. This affects habitat atmosphere design. Pure oxygen at lower pressure reduces mass but increases fire danger, as history has taught painfully. Mixed atmospheres are safer but require more gas. Fire on Mars is a nightmare scenario. In a sealed habitat, fire consumes oxygen, produces toxic smoke, damages systems, and can force evacuation into an environment where evacuation is barely possible. Fire safety affects material choices, oxygen levels, electrical design, emergency procedures, and crew training. On Earth, you can leave a burning building. On Mars, outside is not safe. The habitat must prevent fire and contain it quickly. This is why every object inside a Mars habitat matters. Fabrics, plastics, wires, batteries, food packaging, cleaning supplies, experiment materials, and personal items all need to be considered. A careless spark, overheated device, or chemical reaction could become a mission-threatening event. Comfort items are important, but nothing can be casual. Suits, rovers, airlocks, and habitats form a chain. A weakness in one weakens all. If suits are unreliable, exploration is limited. If airlocks waste too much gas, EVAs are costly. If rovers cannot be repaired, distance shrinks. If habitats cannot manage dust, everything degrades. Survival on Mars is therefore not just about a base. It is about interfaces. The boundary between body and suit, suit and airlock, airlock and habitat, habitat and rover, rover and landscape. Every boundary must work again and again because Mars is always waiting outside. Food on Mars is not only a supply problem, it is a question of whether humans can bring part of Earth's biosphere with them and keep it alive. At first, astronauts would eat packaged food, carefully prepared meals, dehydrated ingredients, thermostabilized foods, bars, powders, supplements, and maybe some fresh items during the earliest part of the mission. This is practical for short durations. But stored food has limits. Vitamins degrade. Menus become repetitive. Packaging creates waste. Mass becomes expensive. And psychologically, eating only preserved food for years is hard. Fresh food matters. A tomato grown on Mars would not only provide nutrients, it would provide color, smell, texture, and emotional connection. A small greenhouse could become one of the most important places in the settlement, not because it produces all calories immediately, but because it reminds the crew of Earth. Humans are not machines. We need symbols of life, but growing food on Mars is extremely difficult. Plants need pressure, temperature, water, nutrients, light, and protection. They do not care that the landscape outside is dramatic. They care about root chemistry, humidity, carbon dioxide concentration, photoperiod, disease, and minerals. A Mars greenhouse is therefore a laboratory and a farm at the same time. Light is a major design choice. Natural sunlight on Mars is weaker than on Earth because Mars is farther from the sun. Dust storms can reduce it further. Greenhouses could use sunlight through shielded panels or mirrors, but radiation and heat loss complicate transparent structures. Artificial lighting gives control, but uses power. A settlement may combine both, using sunlight when available and LEDs when needed. LEDs can be tuned to wavelengths plants use efficiently, but large-scale food production would require significant energy. Water must be recycled through the greenhouse carefully. Plants transpire water into the air, which can be condensed and reused. Nutrients must be supplied and balanced. Human waste, plant waste, and inedible biomass can become inputs after treatment. Composting on Mars may require controlled microbial ecosystems. Microbes are essential for breaking down organic matter, but they also introduce contamination risks. The farm is a living system inside a life support system. Crop choice matters. Early Mars crops would likely favor reliability, nutrition, fast growth, and efficient use of space. Potatoes, wheat, soybeans, peas, lettuce, tomatoes, sweet potatoes, and algae or other microorganisms might all be considered in different systems. Leafy greens provide freshness, but not enough calories alone. Staple crops provide calories but require more space and processing. Algae can produce protein and oxygen efficiently, but may not satisfy human desire for familiar meals. A balanced Mars diet must provide calories, protein, fats, carbohydrates, vitamins, minerals, fiber, and psychological satisfaction. If the crew lacks certain nutrients, health suffers. If food becomes monotonous, morale suffers. Cooking itself becomes important. Shared meals create culture. A Mars settlement that cannot make food feel human may survive physically while becoming emotionally barren. Agriculture also raises the question of pollination. Some crops need pollinators, vibration, manual pollination, or air movement. Bees on Mars would be complicated and perhaps unrealistic early on. Humans may need to pollinate plants manually or use mechanical systems. Even this small detail shows how much Earth does for us automatically. On Earth, entire ecosystems support our food. On Mars, every ecological service must be replaced, simplified, or engineered. Then there is contamination. Planetary protection works in both directions. We do not want to contaminate Mars with Earth microbes in ways that confuse the search for Martian life. We also do not want unknown Martian chemistry or possible biology entering human habitats without control, though no known Martian life has been found. A settlement that grows food must manage biological boundaries carefully. The greenhouse is Earth life on Mars. That is powerful, but it carries responsibility. If life ever existed on Mars, it may have been microbial and perhaps underground. Human settlements could disturb environments that preserve clues to that past. Drilling for water, excavating soil, building habitats, and releasing Earth microbes could complicate science. This means survival and exploration must be balanced with preservation. Mars is not only a future home in some imaginations, it is also a scientific archive. Food waste becomes part of the loop. In a closed environment, leftovers, peels, stems, roots, and human waste cannot simply be thrown away. They are carbon, nitrogen, water, and minerals. Recycling them reduces dependence on Earth. But recycling systems can fail biologically. Too much microbial growth, wrong microbial species, toxins, bad odors, nutrient imbalance, or pathogen survival can create problems. Mars agriculture will require biologists as much as engineers. Long-term, if settlements grow, food production might expand into underground farms, inflatable greenhouses covered with regolith, bioreactors, vertical farms, and perhaps large pressurized caverns. Genetic engineering might produce crops adapted to Mars habitat conditions, not Mars outside conditions, but the indoor conditions available there. Plants might be selected for low pressure tolerance, efficient growth under LED light, compact roots, high nutrient density, and resistance to disease. The dream of walking through a Martian forest is far beyond early missions, but the first green leaf grown from Martian resources would be historic. It would mean that Earth life had not merely visited Mars. It had begun to cycle there, however artificially. That may be the real threshold between exploration and settlement. Not the first footprint, the first harvest. Power decides everything on Mars. A habitat without power is not a home. It is a container losing its battle against the planet. Power runs oxygen systems, heaters, pumps, computers, lights, communications, water recycling, medical equipment, food production, air circulation, pressure monitoring, navigation, manufacturing, and science instruments. It charges rovers and suits. It keeps batteries warm. It supports emergency shelters. It turns a dead shell into a living environment. Solar power is attractive because sunlight is available and solar panels are proven technology. Many Mars missions have used solar energy successfully, but human survival requires more than occasional success. Solar panels on Mars face reduced sunlight compared with Earth. Dust accumulation, seasonal changes, and dust storms. A robotic rover can sometimes hibernate, reduce operations, or die heroically after exceeding its mission. A human base cannot do that. It must keep people alive through the worst conditions. Dust storms are often misunderstood. Mars dust storms can become global, but because the atmosphere is thin, The wind pressure is not like a Hollywood hurricane. A person would not be blown away by a Martian storm the way movies sometimes suggest. The danger is not mainly force. The danger is darkness, dust, abrasion, static electricity, and reduced solar power. A dust storm can turn the sky opaque, coat panels, disrupt operations, and reduce visibility. Even after the storm, dust may remain on equipment. Cleaning solar panels becomes a maintenance task. Robots might brush them. Electrostatic systems might repel dust. Panels might tilt to shed dust. Compressed gas is precious, so blowing dust away may be costly. Human crews might clean arrays during EVAs, but that exposes them to risk. A solar-powered base needs enough storage to survive low light periods and enough margin to recover afterward. Nuclear fission offers steady power. NASA and other organizations have studied small surface fission systems for the Moon and Mars. A compact reactor could provide continuous electricity independent of sunlight. It could run through dust storms and nights. It could support oxygen production, water extraction, heating, and industry. For a serious Mars settlement, nuclear power may be not just helpful, but necessary. But reactors must be landed, deployed, shielded, cooled, and operated safely. Waste heat must be managed. The reactor might be placed at a distance from the habitat for radiation safety, requiring cables and perhaps robotic deployment. If something goes wrong, astronauts need procedures that do not expose them unnecessarily. A reactor is a powerful answer, but not a simple one. Energy storage is equally important. Batteries, fuel cells, regenerative fuel cells, compressed gases, thermal storage, or chemical fuels could help buffer power supply. If oxygen and hydrogen are produced from water, they can be stored and recombined in fuel cells to produce electricity and water. This creates an energy loop, but electrolysis and storage systems require equipment and efficiency trade-offs. Every storage system has mass, losses, failure modes, and maintenance needs. Power also enables in situ resource utilization, or ISRU. This phrase means using local resources instead of bringing everything from Earth. On Mars, ISRU could include producing oxygen from carbon dioxide, extracting water from ice, making fuel, producing building materials from regolith, manufacturing spare parts, and perhaps making plastics or metals eventually. ISRU is the difference between camping and settling. But ISRU is not magic. It requires power, lots of power. Consider making return propellant. If a Mars ascent vehicle uses methane and oxygen, one pathway is to bring hydrogen from Earth or extract it from Martian water. Combine it with carbon dioxide from the atmosphere through the Sabatier reaction to make methane, and produce oxygen through electrolysis or CO2 splitting. This is chemically possible, but it requires reactors, compressors, catalysts, heat management, purification, storage, and months of operation. The propellant plant may be one of the most important machines on the planet. If a settlement grows, industry becomes power hungry. Making bricks, metals, glass, plastics, habitats, pressure vessels, roads, landing pads, and radiation shields requires energy. Mars has raw materials, but raw materials are not useful until processed. Smelting metal from ore, extracting useful chemicals, sintering regolith, producing cement-like materials, and manufacturing electronics are complex. Early settlements will import high-tech components. Over time, local manufacturing may expand, but each step up the industrial ladder demands more power. Landing pads are a good example of an overlooked need. Rockets landing on dusty ground can blast debris at high speeds, damaging nearby equipment. A serious base may need prepared landing zones, perhaps made from sintered regolith, tiles, or constructed surfaces. Building those pads requires machinery and energy before frequent traffic becomes safe. Again, infrastructure comes before expansion. Power also affects location. Near the equator, solar power is stronger and temperatures are milder. Near ice deposits, water access improves. Near scientifically interesting regions, exploration value increases. Near flat terrain, landing and construction are easier. Near natural shelter like lava tubes, radiation protection may improve. But no site gives everything. Energy, water, safety, science, and engineering pull the settlement in different directions. A true city on Mars would need a grid, multiple power sources, storage fields, distribution lines, backup systems, emergency batteries, and perhaps underground cables protected from temperature swings and dust. It would need technicians, robots, monitoring software, and spare parts. Power failures would be treated with the seriousness of medical emergencies. On Earth, electricity can feel invisible. It is there until it is not. On Mars, power would never be invisible. It would be watched constantly. Every watt would have a purpose. Every system would have priority levels. During an emergency, non-essential loads would shut down automatically. Lights might dim. Greenhouse growth might slow. Science instruments might pause. The habitat would protect life first. This is the practical heart of Mars survival. Not flags, not footprints, power. A Mars base is alive only as long as energy flows through it. Mars is often described as a backup planet, but that phrase can be misleading. A backup is something you can use when the original fails. Mars is not ready to function that way. It is not a spare Earth sitting nearby. It is a hostile world that would require immense effort to support even a small number of people. If Earth suffered a catastrophe tomorrow, Mars could not rescue civilization. Not now, not for a very long time. The idea of Mars as a backup only makes sense across centuries of development, not as an emergency exit. This matters because it changes how we think about settlement. If the goal is science, then small research bases make sense. If the goal is inspiration, human footprints may be enough for a generation. If the goal is long-term survival of humanity, the challenge is far larger. A self-sustaining settlement must be able to survive, even if supply from Earth stops. That means producing food, water, oxygen, power, spare parts, tools, medicines, building materials, electronics, and eventually new habitats. It means raising children safely. It means educating them. It means maintaining culture, governance, health, and technical knowledge. It means becoming a society, not just a mission. Self-sufficiency is extremely hard. Even Earth countries with vast resources depend on global supply chains. A single smartphone contains materials, components, and manufacturing steps from around the world. Modern medicine depends on complex chemical industries. Computers require semiconductor fabrication, ultra-pure materials, precision machinery, and enormous infrastructure. A Mars settlement with hundreds or thousands of people would still depend on Earth for many high-tech components for a long time. This does not mean settlement is impossible. It means the path is gradual. The first crews survive. Later crews expand capability. Robots prepare sites. ISRU systems produce oxygen and water. Greenhouses grow some food. Manufacturing begins with simple parts. Regolith becomes shielding and construction material. Power capacity increases. More habitats arrive. Eventually, local production reduces dependence on Earth. But full independence is not a single milestone. It is a long process of replacing imported dependencies one by one. Governance becomes important too. Who makes decisions on Mars? Earth-based agencies, private companies, international coalitions, the crew commander, a local council. What happens when Earth instructions conflict with local survival needs? Communication delay already pushes autonomy. Over time, a Mars settlement would develop its own priorities. The farther and more permanent it becomes, the more it stops being simply an outpost and starts becoming a community. Law matters. Property rights, resource use, planetary protection, emergency authority, labor rules, medical decisions, reproduction policies, conflict resolution, and environmental ethics all become real questions. Space treaties provide broad principles, but a lived settlement would test them in ways no document can fully anticipate. On Mars, governance is not abstract. Bad decisions can kill. Culture would emerge. People would develop routines, language shortcuts, traditions, jokes, fears, anniversaries, and rituals. The first sunrise after landing, the day the greenhouse produced its first meal, the first dust storm survived, the first child born, if that ever happens, the first death on Mars, which would be a profound and painful moment. How do you bury someone on a planet where the ground is frozen, dry, and scientifically protected? Do you return remains to Earth? Do you create memorials inside habitats? Settlement is not just engineering, it is everything human. Economics is another challenge. What does Mars produce that justifies the cost? Science data, technology development, inspiration, and long-term survival may be enough for government missions, but cities need ongoing economic logic. Some imagine mining, but shipping raw materials from Mars to Earth is unlikely to be economical for most resources. Mars may instead produce value through research, intellectual property, extreme environment technology, robotics, closed-loop life support, or serving as a base for further exploration. Its greatest economic value may be not what it exports physically, but what it teaches. There is also an ethical question. Should we settle Mars if there is a chance of native Martian life? If life exists underground, even microbial life, it would be one of the greatest discoveries in history. It would represent a second origin of life, or perhaps a shared origin through ancient meteorite exchange. Contaminating such life with Earth organisms would be a tragedy. Before large-scale settlement, we need to understand Mars better. Human survival and scientific responsibility must be balanced. Terraforming is often proposed as the ultimate solution. Make Mars more Earth-like, thicken the atmosphere, warm the planet, release greenhouse gases, melt ice, create pressure, and maybe eventually oxygen. But terraforming Mars is far beyond current capability. Mars may not have enough easily accessible carbon dioxide to create a thick atmosphere. Its low gravity and lack of a global magnetic field complicate atmospheric retention over long times. Producing an oxygen-rich atmosphere would likely require enormous biological and industrial processes over thousands of years or more. Terraforming is not a near-term survival plan. It is a speculative planetary engineering dream. Paraterraforming may be more realistic. Instead of transforming the whole planet, humans build enclosed environments, domes, tunnels, covered valleys, underground cities, pressurized caverns. These are local Earth-like spaces on Mars, easier than changing the entire atmosphere. A future Martian civilization might consist of many connected habitats rather than open-air cities. People may live under regolith and glass, not beneath a breathable sky. This gives a more realistic answer to the Mars dream. Humans may not live on Mars the way we live on Earth. They may live inside Mars, inside habitats, under the surface, within engineered ecosystems. The planet outside remains alien, while human life exists in protected pockets. That may sound less glorious, but perhaps it is more impressive, because it means survival would not come from Mars becoming Earth. It would come from humans learning how to carry Earth carefully, one sealed room at a time. Could Mars ever become comfortable? Not easy, not Earth-like, but comfortable enough that people do not feel like temporary visitors waiting to leave. This is one of the most interesting long-term questions. Early Mars crews would live under mission conditions. Their days would be scheduled, their equipment would be rationed, their risks would be high, their personal space would be limited. Everything would feel like a spacecraft. But over time, if settlements grew, the goal would shift from survival to quality of life. Comfort begins with space. Humans need room. Not endless room, but enough to avoid feeling trapped. A small habitat may be tolerable for months. For years, people need private sleeping areas, shared social spaces, exercise rooms, medical rooms, workshops, greenhouses, storage areas, quiet zones, and places that feel different from one another. Monotony wears on the mind. Architecture becomes psychology. Light matters too. Mars sunlight is weaker and the sky is different. Inside habitats, lighting would need to support circadian rhythms. The Martian day is close to Earth's, which is helpful, but artificial lighting can still affect sleep and mood. Warm light in the evening, bright light in the morning, simulated windows, seasonal cycles, and visual variety could all help. The goal is not just to see, it is to feel time passing naturally. Sound matters. A habitat full of fans, pumps, compressors, filters, and machinery can become noisy. Constant noise increases stress and harms sleep. Engineers must design quiet systems or isolate loud equipment. Silence is also important. On Mars, true outside silence may be inaccessible, but interior quiet can be created. A library, meditation room, chapel, music space, or simply a quiet corner might matter more than mission planners expect. Smell matters. In sealed habitats, odors linger. Human bodies, food, machinery, plastics, cleaning agents, plants, waste systems, and dust all create smells. Air filtration is life support, but it is also comfort support. Fresh plant smells from a greenhouse could have deep emotional value. The smell of soil, leaves, bread, or cooked food might become part of Martian culture. Exercise will be central. In reduced gravity, people need resistance training, cardiovascular work, flexibility, and perhaps artificial gravity exposure if available. Exercise is not only medical, it reduces stress, creates routine, and gives the body a sense of strength. A Mars gym would be one of the most important rooms in the settlement. Community design matters. Early crews are selected teams. Settlements are communities. Communities need conflict resolution, privacy, friendship, romance policies, family policies eventually, shared celebrations, work-life balance, and ways to handle grief. On Mars, interpersonal conflict cannot be escaped easily. You cannot move to another city casually if there is only one settlement. Social systems must be designed as carefully as mechanical systems. Education becomes important if children ever live there. A child on Mars would need schooling, play, physical development monitoring, connection to Earth culture, and a sense of identity. Would they feel Martian? Would Earth feel like a homeland, a myth, or a dangerous high-gravity world they may never visit? A person born on Mars might not be able to comfortably live on Earth if their body develops under lower gravity. That possibility is profound. Settlement could eventually create humans who are biologically and culturally tied to Mars. Art will follow. People will paint Mars, write Mars music, tell Mars stories, make Mars myths. The first generation may focus on survival, but humans bring meaning everywhere. The red landscape, the tiny Earth in the sky, the long dust storms, the buried habitats, the first greenhouse harvest, the fear of air leaks, the sound of pumps at night, all of it becomes material for culture. Religion and philosophy may change too. Standing on another planet, seeing Earth as a distant light, knowing every human being who ever lived came from that point, could alter how people think about existence. Mars might make Earth feel more precious, not less. The first settlers may not feel they have escaped Earth. They may feel they understand Earth for the first time. Comfort also requires trust. People must trust the habitat, the leadership, the maintenance schedule, the emergency systems, and each other. Trust is built through transparency, training, competence, and repeated success. If systems fail often, anxiety rises. If leadership hides problems, trust collapses. A Mars base cannot function with denial. Reality must be faced quickly. Over decades, comfort might include larger underground spaces, gardens, schools, workshops, communal dining halls, observatories, art studios, clinics, and maybe low-gravity sports. People might create pressurized tunnels connecting modules so they do not need suits for every movement. Rovers might become buses. Greenhouses might become parks. Radiation-shielded windows might offer views of the red horizon. The settlement might develop neighborhoods, not just modules. But even then, Mars remains outside. The doors still open to a lethal world. Maintenance never ends. Dust never stops being a problem. Earth never becomes close. Comfort on Mars would always be earned, never given. That may be the defining difference between Earth and Mars. On Earth, life support is a planet. On Mars, life support is a responsibility. Science is one of the strongest reasons to send humans to Mars. Robots are excellent explorers. They do not need air, food, sleep, or psychological comfort. They can operate for years in places humans cannot safely go. Mars rovers have transformed our understanding of the planet. They have found evidence of ancient water, studied rocks and chemistry, measured radiation, tested technologies, and shown us landscapes no human has yet seen in person. But humans bring flexibility. A trained geologist can notice patterns, make decisions, adjust plans, and interpret context quickly. A human crew with tools, mobility, and laboratories could do in weeks what robots might take years to accomplish. Mars is scientifically compelling because it was once more Earth-like. Ancient river valleys, lake beds, deltas, minerals formed in water, and sedimentary rocks all suggest that billions of years ago, Mars had environments where liquid water existed at the surface. The biggest question is whether life ever arose there. If life did arise on Mars, even microbial life, it would be one of the most important discoveries ever made. It would tell us that life is not unique to Earth. If Mars had habitable environments and life never appeared, that would also teach us something profound about how difficult life may be to start. Human explorers could drill, sample, analyze, and travel in ways robots cannot yet match. They could search ancient lake deposits, hydrothermal minerals, buried ice, lava tubes, and subsurface environments. They could select the most promising rocks for return to Earth, or analyze them in advanced laboratories on Mars. They could respond to unexpected findings immediately. The scientific value could be enormous. But science and survival can conflict. The best scientific sites may not be the safest settlement sites. A place with ancient sediments may not have easy water ice. A place with accessible ice may not preserve the best biosignatures. A flat, safe landing zone may be far from the most interesting geology. Mission planners must balance science, safety, resources, and engineering. Planetary protection complicates human science. Humans carry microbes. Even the cleanest spacecraft cannot be sterile once humans are involved. If astronauts explore regions where Martian life might exist, they risk contaminating samples or environments. This is especially important for possible subsurface habitats, recurring brines, ice deposits, or caves. We want to search for Mars life without accidentally bringing Earth life into the evidence. This may mean establishing zones. Some regions might be protected for robotic astrobiology before humans approach. Human bases might be located away from the most sensitive sites. Samples might be handled in sealed systems. Drilling equipment might be sterilized. Waste management would be strict. The more humans live on Mars, the harder it becomes to keep Mars pristine. This does not mean humans should never go. It means we should go carefully. Mars also teaches climate science. It is a planet that appears to have changed from warmer and wetter to cold and dry. Understanding how it lost its atmosphere, how its magnetic field disappeared, how water moved into space or underground, and how climate evolved can help us understand planetary habitability in general. Earth, Venus, and Mars form a powerful comparison. Venus became a runaway greenhouse world. Mars became a frozen, thin atmosphere world. Earth remained habitable. Studying Mars helps us understand why. The geology of Mars is also spectacular. Olympus Mons is the largest volcano in the solar system. Valles Marineris is a canyon system thousands of kilometers long. Ancient impact basins, lava plains, polar caps, layered deposits, dust dunes, and possible cave systems make Mars a world of deep history. Human explorers would not merely survive there, they would read the planet like a book. Mars may also preserve records that Earth has erased. Earth's active plate tectonics, weather, oceans, and biology recycle surface materials. Mars is more geologically quiet in many ways. Ancient rocks may remain accessible for billions of years. They may preserve the early solar system, ancient atmospheres, impact history, and maybe prebiotic chemistry. Mars could be a museum of planetary time, but surviving long enough to do that science requires discipline. Every EVA must balance curiosity with safety. The most interesting rock may be just beyond a safe distance. A dust storm may interrupt a traverse. A suit warning may force return. A sample may be scientifically priceless but contaminated. Exploration on Mars would require humility. The planet will not care about human excitement. Science also provides meaning for crews. Maintenance keeps them alive, but discovery gives purpose. A crew that spends years in danger needs reasons beyond survival. Finding evidence of ancient water, sampling a possible biosignature, drilling into ice, mapping a cave, or watching a sunrise from a ridge could become moments that justify the hardship. Humans endure more when they believe their effort matters. If a Mars crew found strong evidence of past life, the emotional impact would be enormous. Imagine a tiny fossil structure, an organic pattern, an isotopic signature, or a microbial trace preserved in ancient rock. The first proof that life began twice in one solar system would change biology, philosophy, religion, and our place in the universe. It would mean life may be common wherever conditions allow. If they found no life after decades of searching, that too would be haunting. It might mean that habitable conditions are not enough, that life is rare, that Earth is even more precious. Mars would become a silent witness to a possibility that never happened. Either way, Mars has something to tell us. And perhaps humans are drawn to it because, somewhere beneath the survival problem, Mars is also a question about ourselves. Are we the kind of species that stays where it is safe? Or the kind that crosses impossible deserts to learn what happened there? Terraforming Mars is the dream that refuses to disappear. The idea is simple to say and almost impossible to do. Warm Mars, thicken its atmosphere, melt its ice, create rivers, lakes, clouds, rain, perhaps eventually oxygen. Turn the red planet into a second blue world. In science fiction, terraforming is often treated as the natural long-term destiny of Mars. Humanity arrives, struggles, builds, and eventually changes the planet itself. But real Mars is stubborn. To make Mars comfortable for humans without suits, we would need at minimum a much thicker atmosphere, higher surface pressure, warmer temperatures, and breathable oxygen. Each of those requirements is enormous. Warming the planet might be possible in theory with greenhouse gases, mirrors, orbital infrastructure, industrial activity, or engineered compounds. But warming alone is not enough. Pressure matters. Humans cannot walk outside safely if water cannot remain liquid and lungs cannot function. A thick atmosphere requires gas. Where does that gas come from? Some carbon dioxide exists frozen at the poles and absorbed in the soil or minerals, but studies suggest that easily accessible CO2 may not be enough to create an Earth-like atmosphere. Even if all available CO2 were released, Mars might still remain far too thin for humans. Importing volatiles from comets or asteroids is sometimes proposed, but that requires moving enormous masses across the solar system. Manufacturing greenhouse gases on Mars would require vast industry. None of this is near term. Then there is gravity. Mars has lower gravity than Earth, which makes it harder to hold on to atmosphere over geological time. The lack of a global magnetic field also means the solar wind can interact with the upper atmosphere more directly. Atmospheric loss is not instant, but over long periods it matters. Terraforming would need not only creation, but maintenance. Oxygen is even harder. Earth's oxygen-rich atmosphere was created by life over billions of years, especially photosynthetic organisms. Producing breathable oxygen on Mars would require enormous amounts of photosynthesis or industrial oxygen production. But oxygen also reacts with rocks and soils. Before it accumulates in the atmosphere, it can be consumed by chemical reactions. Creating an oxygen atmosphere is not just filling a tank, it is changing a planet's chemistry. Liquid water on the surface would require pressure and temperature stability. If Mars warmed somewhat but pressure remained low, water would still be unstable. If pressure increased but temperatures varied wildly, water might freeze or evaporate seasonally. A stable hydrological cycle would require planetary-scale transformation. There is also the ethical issue. If Mars has native life, terraforming could destroy it. Even if Mars life is only microbial and underground, changing the planet for human comfort could erase an independent biosphere. Before terraforming, we would need to know what Mars is biologically. The moral question is enormous. Does humanity have the right to transform a planet that may preserve another origin of life? What if that life is dormant? What if it exists only in isolated underground pockets? What if we cannot know for sure? For all these reasons, terraforming is not a survival plan for early Mars. It is too slow, too uncertain, too large, and too ethically complex. The first humans on Mars will not stand under a thickened sky. They will stand in suits. Their habitats will be sealed. Their farms will be indoors. Their children, if children ever come, will grow up inside engineered environments. not open fields. A more realistic intermediate idea is para-terraforming. This means creating habitable environments locally rather than changing the whole planet. A covered crater, a pressurized valley, a network of underground tunnels, a dome, though likely not the fragile glass kind people imagine, a lava tube converted into a town, a greenhouse complex shielded by transparent water layers or advanced materials. These spaces could grow over time, connecting into larger human environments. Para-terraforming accepts Mars as it is. It does not require the entire atmosphere to change. It builds islands of habitability. That may be how Mars becomes livable, not as one transformed planet, but as many protected worlds inside the larger hostile world. Over centuries, these protected spaces could become extensive. Imagine a settlement inside a lava tube, with pressurized chambers, farms, workshops, homes, schools, and recreation areas. Outside, the surface remains cold and thin-aired. Inside, children play under artificial sunlight. People walk without suits. Trees grow in carefully managed soil. Water cycles through tanks, plants, and air. The settlement is not Earth, but it contains pieces of Earth. This may be less visually grand than terraforming, but it is far more plausible. It is also more controllable. If a local habitat fails, repairs are possible. If a greenhouse has a disease outbreak, it can be isolated. If a dome cracks, sections can be sealed. Planet-wide terraforming has no easy emergency shutoff. Still, the dream of an open-air Mars will remain. Humans are drawn to horizons. We do not merely want to survive behind walls. We want landscapes that welcome us. We want to breathe outside. We want rain. We want wind that does not kill. We want rivers. The tragedy of Mars is that it looks like a place where those things should be possible, because maybe they once were. Ancient Mars may have had rivers and lakes. Perhaps long ago, Mars was closer to habitable than it is now. Terraforming is partly a desire to restore something the planet lost. But the Mars we can reach is not ancient Mars. It is modern Mars. Cold, dry, thin, irradiated, dusty, and silent. So, if humans survive there, it will not be because Mars becomes gentle. It will be because we learn how to be careful. There is one question that sits quietly beneath every Mars plan. Would people really want to live there? Not visit, not make history, not spend a heroic mission collecting samples and returning home. Actually live there. Wake up there year after year, work there, age there, maybe die there. The answer will not be the same for everyone. Some people would never want it. Earth is too rich, too alive, too beautiful, too comfortable. Others would feel drawn to Mars with a force that is hard to explain. The first settlers of any frontier are often motivated by a mixture of curiosity, ambition, desperation, belief, and willingness to accept hardship. Mars would be the most extreme frontier humans have ever attempted. But we should be careful with frontier language. Earth frontiers were never empty in the way people often imagined, and human expansion on Earth came with violence, exploitation, and ecological damage. Mars is different because it has no known civilization, but the language of conquest can still be dangerous. Mars should not be treated as a prize to be consumed. It is a world with scientific value, history, and perhaps unknown biological significance. Living there should begin with respect. For the people who go, daily life may be less glamorous than the first landing. Much of survival is maintenance. Checking seals, cleaning filters, inspecting suits, testing air quality, repairing pumps, managing inventory, exercising, logging radiation exposure, cleaning dust, growing food, monitoring water systems, updating procedures, doing science, resting, repeating. Mars life would be built from routine. Routine can be beautiful. A crew that knows its systems, trusts its work, and sees progress can find meaning in repetition. On Mars, ordinary tasks become extraordinary because of where they happen. Fixing a valve may save lives. Harvesting lettuce may feel like a miracle. Watching a dust storm from a shielded window may become a memory carried forever. The first cup of coffee brewed from recycled water on Mars might mean more than a banquet on Earth. But the hardships are real. Homesickness would be intense. Messages from loved ones arrive delayed. Birthdays happen across planets. Earth news comes from far away. Family emergencies cannot be attended. A parent may grow old while an astronaut is away. A child may be born on Earth while a crew member is millions of kilometers distant. Mars exploration asks not only technical sacrifice, but emotional sacrifice. The view of Earth from Mars could become one of the most powerful images in human history. From Mars, Earth is a bright star-like object. Everything familiar is contained in that point. Oceans, forests, languages, wars, music, cities, animals, families, all of history. Astronauts on the Moon described the overview effect, a shift in perspective when seeing Earth from space. Mars may create something deeper, the distance effect. Earth not as a globe filling the window, but as a small light that cannot be quickly reached. This may make Earth feel more fragile. Ironically, going to Mars may teach humanity to value Earth more. Mars shows what a planet without a thick, breathable atmosphere, liquid surface water, global biosphere, and protective magnetic environment looks like. It is not a replacement. It is a warning and a challenge. Earth is not ordinary. Earth is the most habitable world we know. Some people argue that we should fix Earth before going to Mars. Others argue that exploring Mars can help us fix Earth by advancing technology, inspiring cooperation, and reminding us how rare habitable planets are. These are not mutually exclusive. We can care for Earth and explore space. In fact, a civilization mature enough to live on Mars must also be mature enough to protect its home planet. If we cannot manage Earth's life support systems, building artificial ones on Mars will be much harder. Mars survival may become a mirror. It forces us to ask what life needs: air, water, pressure, temperature, food, community, purpose, protection, energy, waste recycling, governance, humility. These are the same things civilization needs on Earth, but Earth provides many of them quietly. Mars makes them visible. A person living on Mars would become intensely aware of dependence. Dependence on machines, teammates, stored supplies, power systems, Earth launches, and planetary cycles. But perhaps all humans are dependent in similar ways. We depend on forests, oceans, microbes, climate, agriculture, sunlight, and one another. Mars strips away the illusion of independence. Would humans survive there? Yes, in the technical sense, if we build well enough, prepare carefully enough, and accept enough risk. Would humans thrive there? That is harder. Thriving requires more than staying alive. It requires meaning, health, relationships, beauty, growth, and a future that feels worth choosing. Early Mars crews may thrive because their mission gives them purpose. Later settlers would need a deeper kind of life. The first humans on Mars will be explorers. The first people who stay will be builders. The first people who call it home will be something new. Now let's answer the question directly. Could humans actually survive on Mars? Yes, but only inside a chain of technologies so complex that it almost becomes a second biosphere. Humans could survive on Mars if they have pressurized habitats, reliable oxygen, clean water, radiation shielding, thermal control, power, food systems, medical care, dust management, spare parts, communication, mobility, emergency shelters, and the discipline to maintain all of it. Mars survival is possible, but it is conditional. The conditions are everything. A person cannot survive Mars. A system can. That distinction matters. When people ask whether humans can live on Mars, they sometimes imagine human toughness as the deciding factor. But toughness is not enough. No amount of bravery lets you breathe carbon dioxide at near vacuum pressure. No amount of optimism blocks cosmic radiation. No amount of training makes crops grow in untreated toxic dust under an unpressurized sky. Mars does not reward confidence. It rewards preparation. The first missions will likely be fragile, not because the astronauts are weak, but because early systems are limited. Every kilogram matters. Every spare part matters. Every EVA has risk. Every dust storm matters. The first crews will live close to the edge compared with later settlements. They will be pioneers, not because they carry flags, but because they accept that their safety margin is built from equipment that has never before supported humans on another planet. Over time, survival could become easier. More habitats, more power, better shielding, local water extraction, oxygen plants, food production, manufacturing, medical capability, pressurized rovers, buried structures, larger crews, better psychology, more experience. The danger does not disappear, but the settlement becomes more resilient. The difference between an expedition and a community is redundancy. The long-term dream depends on closing loops. Water recycled almost completely, air regenerated, food grown locally, waste reused, materials processed, parts manufactured, knowledge preserved, children educated, systems repaired without Earth. This is hard, but every step toward it teaches us how life support works. Mars may become the greatest laboratory for sustainability ever built, because wastefulness there is not merely unethical. It is impossible. And yet, even if humans survive on Mars, it may never be easy. It may always be a world of walls and procedures. The outside may always require suits. The settlements may always depend on power. The dust may always return. The radiation may always shape architecture. Earth may always remain the deeper home, the place where humans can stand under rain without machinery. That does not make Mars meaningless. It makes it honest. Mars is not attractive because it is easy. It is attractive because it is almost possible. It sits close enough that our machines can reach it, and hard enough that reaching it changes us. It is a test of whether intelligence can build a pocket of life on a dead world. A test of engineering, cooperation, patience, and humility. There is something haunting about that. Imagine the first night inside a Mars habitat. Outside, the sky darkens over red dust. The temperature falls. The air pressure remains almost nothing. Radiation moves silently through space. The wind pushes dust against the walls. Earth hangs somewhere in the sky as a bright point, too far away to help quickly. Inside, fans turn. Pumps move water. Computers monitor oxygen. People sleep in a warm room on another planet. That room would be one of the most extraordinary places in human history. Not because Mars welcomes it, because Mars does not. Every second it exists, it proves that life from Earth can cross the void and endure where it was never meant to be. So yes, humans could survive on Mars. But the deeper truth is that Mars would never let us forget what survival means. And maybe that is why Mars holds our attention so strongly. It is not the best world for us. It is not the easiest world. It is not waiting with oceans, forests, animals, or air. It is a cold red desert beneath a thin sky, filled with ancient clues and modern dangers. It is beautiful, but not gentle. It is close, but not safe. It is possible, but only barely. If humans go there, they will not be conquering Mars in the simple way old stories imagine. They will be negotiating with it, learning its dust, its cold, its silence, its radiation, its seasons, its chemistry, and its limits. They will survive by respecting those limits. They will build carefully. They will recycle obsessively. They will repair patiently. They will watch every pressure reading and power level. They will become the caretakers of a tiny Earth-like flame, burning inside a world that cannot feed it. And if that flame lasts, if the habitats grow, if the greenhouses expand, if children one day learn the names of Martian rocks before they learn the names of Earth oceans, then Mars will have changed the human story forever. Not because it was another Earth, but because it forced us to understand Earth. Every breath on Mars would remind us that air is not guaranteed. Every drop of water would remind us that oceans are miracles. Every green leaf would remind us that life is fragile. Every sealed door would remind us that a habitable planet is not normal. It is rare, delicate, and astonishing. Mars may someday become a home, but it will always be the kind of home that teaches humility. A home where survival is not background. A home where survival is the story.